Swayam Prabha. Digital India. Educated India.
Alright, so in the last few classes we have learnt about the random walk models and how are they used in polymer physics. In today's lecture, what I want to introduce is the idea that the random walk descriptions we have derived have certain similarities with the diffusion equations that you may have learnt in mass transfer or other courses. So just to give you some reminder of the diffusion equation, it looks something like this. Where, for example, in Cartesian coordinates, the del square is like dou 2 by dou x square plus dou 2 by dou y square plus dou 2 by dou z square, and we are solving for the concentration of any species as a function of a spatial location and time. This is what is known as the Fick's law of diffusion. In fact, there are two laws, one that relates the concentration as the derivative of the flux, and another law that basically describes the flux J as diffusivity multiplied by the del of C, and when the two are combined together we get this particular equation. Now you may be surprised that how does the random walk description, where I was looking at probability of certain end-to-end distance, does relate with this particular relation, and we will try to build that in today's lecture. And basically the equations that we will show will have mathematical similarities with these equations, and then we can talk about analogy of the variables you see in this equation with whatever equation we will derive. So let us say I am looking at a z dimensional random walk it's a bit of a misnomer. So when I say a z dimension, it is not a physical dimension. What z means is the number of available directions for every segment. So let us say, for example, for the two dimensional walk that we have discussed, the z is equal to 4 because we can move in left, right, up and down and so on. Okay. So if we are doing a z dimensional random walk, and let us say I am at a particular end-to-end displacement RE or end-to-end distance RE, after steps m, we have derived that the probability distribution or the probability density for this particular thing to happen goes like a Gaussian function for an ideal chain. But to be here in m steps, we must be somewhere near it in the previous step. To be more precise, I must be at a position RE minus BI, where BI indicates all available directions for the chain movement. Okay. So let us say, for example, if I am at A, B, C and D in the figure, I can come to the point O in one step, and then we can have this particular distribution. Okay. So, then we can write that the probability that the end to end displacement is R e after m steps, that must be equal to 1 by z sum over I equal to 1 to z P of R e minus B I in m minus 1. What essentially it means, I must be at one of the positions nearby, that is, it can be in any of the z directions, and then if suppose I am at A, I can of course go to any other direction then coming towards O. So, there is a probability of 1 by z that I can go from A to O out of all the possible available directions. Okay. And so, if I extend the idea to all the possible neighbors, we get this particular relation. Okay. So, now if I look at this particular quantity here and assuming that the bond vector is much smaller than R e and m is like much higher than 1, we can Taylor expand the probability that you see here. Okay. So, let us just do that. So, now we have discussed Taylor expansion of one variable. If you look at this particular function, it contains two variables. So, first I will discuss how do we do Taylor expansions in more than one variable, and then we will apply to this particular equation to see what exactly we do get. Okay. So, for Taylor expansion in one variable goes something like this. So, if I want to look at a function value in the neighborhood of x, where h is much smaller than x, this is equal to f of x plus f prime of x evaluated at x multiplied by h plus f double prime of x multiplied by h square by 2 and so on. Now, if we have more than one variable, we can write this as, let us say the variables are x1, x2 and so on, and we are say h1, h2, h3 far from there. It is simple extension of what we derived, what we written just before this for the case of vectors. So, now I will get this equal to, the first term is simply the function evaluated at x1, x2, xn, and now we can take a partial derivative with respect to x1, x2, x3 and so on. So, we have in total n partial derivatives of first order. So, we can write this as sum over j equal to 1 to n dou f by dou x j h of j. The same idea now apply to the second order derivative. Now, second order derivative, if you think about it, it is basically two first order derivatives. So, now I can apply a first order derivative of any of these x, and then I can apply the second derivative for with respect to any of the other x. So, what this comes out to be is basically now two sums, say j equal to 1 to n and L equal to 1 to n, dou 2f by dou xj dou xl hj hl by 2 factorial. So, now let us go back to the relation we have derived for P of REM. We are interested in P of RE minus BI m minus 1, that is the probability distribution for the random walk of m minus 1 steps to have the end to end distance RE minus BI. So, in this particular case, we can think of two variables here. Let us say x1 as my RE and corresponding h1 is equal to minus BI, and then x2 is equal to m and h2 is equal to minus 1. So, if I use this and I use the relation I have just derived, this is equal to P of RE m plus, now we have two derivative, one with respect to RE and one with respect to m. So, we have dou P by dou RE you see a bit of a trick here, that since one of the variable is a vector, the derivative of probability with respect to RE is also a vector, and since the final result is a scalar. So, I take the derivative and I dot with the corresponding value of h. So, the end result is a scalar. Similarly, for m, and now we also will have the second order derivatives. So, now again basically what you have is you have two derivatives now with respect to RE. So, what you have formed is like a tensor, and if you dot with the BI values, again there are two BI values corresponding to 2H, that also is a tensor. So, if you take two dot products, what you end up having is a scalar again. So, this is what we will have, and I will discuss that in a moment. Then what we also have are terms containing something of this sort and something of we only have a BI there, something of this sort, because we have minus 1 squared here, that becomes 1. So, now we will note that in the end for an ideal chain we already have derived that RE scales like square root of m, because RE square goes like m. So, if I look at dou by dou RE of P, that must be much higher compared to the derivative with respect to m, because we have square root of m here and we have m there, they both come in denominator. So, what we can think of is to drop the last two second order derivative, and of course all the third order and higher derivatives. Okay. So, now what we end up having is something like this. Okay. So, now we have some vector derivatives and vector dot products. Before I go into details, I want to discuss a particular notation that is called Einstein notation, that will help us to write these vectors and tensors in very compact form, and we will be using that in the entire course. If you know about the Einstein notation, this is what it is. If you do not know about it, I will discuss that briefly now. So, let us keep this in mind and we will come back to this in a moment. So, in the Einstein notation, if for example, we have a vector v in 3 dimensions, it indeed has 3 components. In Cartesian coordinates, it looks like this. It is of course cumbersome to write. So, in Einstein notation, I will write this as simply V alpha, and this is V alpha is basically the representation for V. Of course, we could have written this also as summation of say V alpha E alpha, where alpha is like x, y, z, that is also cumbersome. I am preferring to write like this, and this is what I will refer to as the Einstein notation. So, alpha you note here is what is referred as a free index. If the alpha is repeated, it is called a dummy index, and I will tell you like how does it happen, this happen. So, let us say if for example, I want to do A dot B, I can do in complete vector notation, as I will decompose the A into 3 terms, and I will dot with the B decomposed in 3 terms, and then we know that all the dot products of unit vectors in different directions which are orthogonal to each other will cancel, like Ex dot Ey is 0, Ex dot Ez is 0, but in the same direction they will dot to 1. So, Ex dot Ex will be equal to 1. So, using that we can get this as Ax Bx plus Ay By plus Az Bz. This is of course again cumbersome to write. Again I could have used a sum alpha is equal to x, y, z, A alpha, B alpha, and this basically means the same thing. If I am using the Einstein notation, it is even more compact. I would simply write this as A alpha B alpha, and this becomes again my Einstein notation. So, in this case alpha is a free index, that means it is not repeated, and in this case alpha is a repeated index or dummy index. Now, the advantage of doing this is I will simply count the number of free indices that are present in the equation, and that will tell me the order of the vector. Let us say for example, in this case there are no free indices. So, the order is 0, that means it is a scalar. In this case there is one free index and the order is 1, that means it is a vector. If for example, I am doing something like A, B, what essentially I mean, if I do not put a dot or a cross product in between, is it is a tensor. In the full notation, again it is rather cumbersome. And then you can see it will have 9 terms. Of this sort, which I can again use in summation form as alpha, beta, both going from x to z, A alpha, B beta, E alpha, E beta. But if I am using the Einstein notation, it is simply which is the Einstein notation for this case. Now, you can see both alpha, beta are free indices, that means the order is 2. So, now we have a tensor of second order. So, I will use this particular relation in the relationship we have just derived and see like what it turns out to be. So, just refer to what we have here and we will focus on these two terms because they contain the vector or tensor. These two terms are anyway straightforward. So, let us first write the scalar terms. And now I should have a term that represents so as I was just telling you, A dot B has to be a scalar if A and B are vectors, and I will represent as A alpha B alpha. That means in this case I will look at the alpha component of the first one and the alpha component of the next one, and this is in Einstein notation the expression. Of course, this means a sum of this particular quantity, but we are not writing the sum here. This is the Einstein notation. Similarly, we had one more term of second order here that you can see. So, let us see what it will become. So, we had second order derivative and then there are two dots which I will write as and there was a divided by 2 here. Again you can see this is now a tensor representing the same tensor we have here. This is again a tensor representing this particular tensor. When I apply the dot product twice, we will have repetition of both alpha and beta which were present as free indices in the two tensors, and that is why the end result contain no free indices, it only has two dummy indices alpha and beta, and so this particular thing is a scalar. Okay. So, let me write that here. So, this becomes in Einstein notation this. Okay. So, now if you go back to the initial relation that we have derived, we had to sum over this. What we were interested in, if you remember, was PREM, and as we had derived earlier, I can write PREM as sum over the quantities that I have just Taylor expanded. So, what I am interested in is 1 by z sum from I equal to 1 to z of this particular quantity. Now, you can see the first term here, if I add it like z times and I divide by z, what essentially I will have is the same thing PREM. The same thing applies for the second term here. For the third term, however, we now have to sum over all the z values, all the values of I which are possible. And now you must note that this must be equal to 0 because the available direction vectors add to 0 in the case of the z dimensional random walk. If you can go in this way, you also have probability of going in the opposite direction, which will be same as in the two cases. Similarly, the probability for this is same as probability for that. So, this term simply cancels out. Now, I can look at the last term, which will be okay. So, now let us look at like what that last term is equal to in detail. So, what we have got so far is P of REM is equal to P of R E m minus dou P by dou m, then the other term was 0, and then in the end we had okay. So, now if I look at this particular term, you should remember from the random walk relation that if alpha is not equal to beta, in this case this must be equal to 0, because the steps in x direction are independent of steps in the y direction or z direction. So, this particular quantity will be equal to 0 when alpha is not equal to beta, and this quantity will be equal to bi alpha squared when alpha is equal to beta. Now, alpha can take values of x, y and z. So, this can be like bi x square or bi y square or bi z square, and for this particular walk in three dimensions, we know that the sum of these three must be equal to b square. So, this particular quantity must also be equal to b square by 3, because the 3 dimensions directions are pretty much equal. So, the b squares in each of the 3 directions must be equal, and then since they all sum to b square, each of them must be b square by 3. Okay. So, I have a shortcut for writing this particular thing, that it is equal to 0 when alpha not equal to beta and is equal to b square by 3 when alpha is equal to beta. As in a shortcut notation, I can write like something like this, where delta of alpha beta is a function I will frequently use. It is called the Kronecker delta, and it is equal to 1 when alpha is equal to beta and equal to 0 when alpha is not equal to beta. And of course, you can see here this is what we have written in this particular case. Okay. So, now if I just do this, what I will end up having is, so you can see here, if I do this, now there are cancellation of this, and then what essentially you will get is minus of dou p by dou m plus something like b square by 6 and the reason why we have got this is because once delta of alpha beta goes here, now the product of that with the secondary order derivative will only be non-zero when alpha is equal to beta, and that is why I have put alpha equal to beta in this particular case, and this is equal to 0. So, that gives me now if I look at the final answer that we have got, and if I compare that to the diffusion equation I wrote in the very beginning, which I can write in one dimension, let us say like this, then I can relate the concentration as being analogous to the probabilities, the time as being analogous to the number of segments m, and d as being analogous to b square by 6, and for the one dimensional case x as being analogous to r e. We can extend the idea, actually r will be analogous to the r e. Okay. So, now apart from this, the solution of this equation will be same as that of a diffusion equation. We have to look at like what the boundary conditions are, and what it turns out is by solving this equation we can also recover the fact that the probability distribution is Gaussian in nature. So, this is, I would say, a more rigorous way of deriving the fact that the probability distribution is Gaussian. The way we have done in the past, we have done it as looking at a one dimensional walk problem, then we got a binomial distribution, and then we took a limit when the number of steps are very large, and then we have got the Gaussian distribution. But we can also get it by using this particular diffusion equation that we have got for the probability. The solution of this will also give you the Gaussian distribution, and this particular concept will be very useful as we will discuss in this course. Thank you.